All right, before we get to our lesson for 1.3, a little warm-up. This is just like the question that you're going to see on your test on Thursday. And I'm going to give you a function that is simply graphed, and you're going to estimate from the graph a couple of things for me. Now, what we find is that kids get thoroughly confused with the notation. So these first three questions are in the same notation. You have to kind of interpret it for me, though. So like, for instance, f of negative 2. Is negative 2 an x value or a y value? That's an x value. So your job is to figure out the output when x equals negative 2. So you go over to x equals negative 2, which, by the way, this is counting by 2s, so be careful. And then you either look up or down to try to find the function itself. So here's negative 2, but here's the actual point itself. So can you tell, I know it's kind of hard in the back, but can you tell what height it's reaching right here? Also negative 2. So that was kind of a coincidence that it had a negative 2 for the output as well. And then this next one, f of negative 6. So again, this is an x value of negative 6. So let's travel over to negative 6. I got to go find the function. Uh-oh, something weird. Notice this time, at negative 6, there is an open circle. So it is what we call undefined at x equals negative 6, because there's nothing up here either. So what you would tell me for an output is that the function does not exist. That's kind of a tricky question. I don't think we're going to do that to you on a test where it doesn't exist. Let's take a look at this one. This is the one that most kids screw up. This is when x equals 0. So I get a lot of kids who are looking over here and they're going, oh, it's about, 6, 7-ish. Is that when x equals 0? X equals 0 is this line right here. So I look up, I look down, uh-oh. Is there a definition for when x equals 0? No. So again, you would say it does not exist. Now, totally separate questions. What if I switch it up and I write the notation like this? It says, find f of x. F of x equals 2. I want you to find x this time. So this is a y value. So if you go to where y equals 2 on your graph, that would be this line right here. Whoops. This time you're supposed to tell me what x value that occurs at. So does that look like 6 to you? Looks like 6 to me. And then how about at x equals negative 6? Sorry, when y equals negative 6. Very tricky question, guys. Why?
Is that in the middle?
Yeah, they're estimations for sure. And how many of them are you going to have to tell me?
2.
There's 2 different x values for which your function equals negative 6. So we'd estimate it. We'd say like about negative 5 maybe. And that one looks a little beyond 7, so I'm going to call it like 7.3. Totally making that up. And if this was a test question, like I'd have to accept whatever relative answer you gave me that were around negative 5 and 7 point something.
What if I put 7.327?
That is a very specific estimate, and I would be very impressed. I think we took careful consideration on your test to make sure they came out fairly nice. So they're either like exact integers, or it's clearly right in the middle, so you're going to call it a 0.5 or something like that. Or, maybe Cameron calls it 0.5138241. Something like that. I don't know. All right, so there's a question on your test that's like this. So you're basing it off the graph, but you really have to focus on, okay, are they giving me an x or are they giving me a y? Am I finding an x or am I finding a y? That's probably, in my opinion, one of the trickiest questions on the test. Okay, here's your lesson. 1.3, continuity, end behavior, and limits. End behavior is an old topic. It's going to feel very familiar to you, and I think all of the Algebra 2 teachers and Honors Algebra 2 teachers teach it the same way now. So we're going to be using the same template that you used last year in Algebra 2 or a couple years ago. Continuity is a newish topic, but it's not really new because we kind of already talked about it 2 lessons ago. And limits is super new because that's a calculus concept. We are going to do a chapter, a very mini chapter on limits at the very end of PreCalc. So today I'm just going to kind of expose you to the notation. And then we're going to decide how we're going to approach the questions, and it won't be through a calculus lens. It'll be through a pre-calculus lens. All right, so this is one of the largest theorems in calculus, and it has to do with whether functions are continuous. So when you move on to a calculus class, they will make you go through this theorem and prove these 3 things. The first thing to prove whether a function is continuous is that for f of x, x equals c exists. So if you were to plug in a number into your function, you actually get a point. So that's what this means. There is a point. Then the second part of the theorem says f of x approaches the same function value from the left side and the right side. And then this is the fancy notation, guys. The limit exists. So what is really quite an easy concept, it looks like this. If I come from the left and I come from the right, it seems to be approaching the same y value. But are there functions out there in the world that don't do that? Have you ever seen something where when you come from the left side, it's a different height than when you come from the right side? We've seen them. They're usually piecewise functions, but we're going to see other kinds too. All right, so basically, from the left side and the right side, the limit exists. And then the third thing is my favorite. Basically, it says number 1 and number 2 match. It's kind of like, at first you're thinking like, well, okay, when would they not match? So sometimes it's easier for me to show you an example of them not matching. What if I had a curve that did this? And then the point was here. And you're like, is there such a thing? And the answer is yes. Wow. So the issue is, so this is what they're calling C. If we just named it like -3, that would work too. So there's totally an ordered pair at -3. It's up here. It's like -3, 5. I'm making these numbers up. So that's number 1. Check. Number 2 says if I approach it from the left side and the right side, it's approaching the same value. I would have to make this up too. Let's pretend this is like a height of 2. So it's approaching a height of 2 from the left side and the right side. But it does not match, right? The height of the point and the height of the limit are 2 different values, and this would be considered a discontinuous function. Now guys, we didn't have to go through all that math for you to look at that graph and go, yeah, that's not continuous. There's a hole in it. That would be a problem, okay? So for us in PreCalc right now, you guys are looking for pictures of discontinuity at first. So if you see a hole, a jump, later we're going to see oscillations perhaps, breaks of any sort, clearly it's a discontinuous function. But what I want you guys to focus on are some of the major types of functions that we're going to work with, like piecewise functions and rational functions, and having algebraic ways to determine whether or not they're continuous. Because I'm going to show you a piecewise function in a minute, and the first thing I'm going to ask you is, do you remember how to graph it? And while your answer might be yes, my next question is, do you want to graph it? And your answer will be no. You don't want to graph piecewise if you don't have to. No one likes them. Except for math teachers, but we're weird. Alright, so this is again the key concept to a limit, and then whether a function is continuous or not has to do with the verbiage of, does the limit exist? You guys don't have to worry about those words. We're not going to ask you to prove any limits today. What I am going to ask you to do is notify yourself, yes, indeed, this is discontinuous. So for instance, this is from your textbook. Looking at this picture, can you confirm for me that that is most definitely not continuous? It is not a smooth curve. There's a break right here. There's a vertical asymptote that interrupts your domain, and therefore it's not continuous. You're pretty good on telling me this one's not continuous? There's a huge break in the middle. This is what usually piecewise functions look like for you guys. And then you probably never encountered this unless you did a little bit of extra work in Honors Algebra 2 or you took college algebra. But there are what are called rational functions that produce what are called removable discontinuities. We call them holes. They literally are holes. So at that point, the function does not exist, and therefore it's not continuous. That's a lot of words. So let's talk about what we have to do for PreCalc. This is really a calculus concept. This might be a problem Mrs. Gupta would give you next year. So we have an absolute value function, 2 times absolute value of x plus 3, and they want to know if it's continuous at x equals 2. Now, to a PreCalc student, you should say to yourself, what does an absolute value function look like? And you'd be like, it looks like that. Are there any interruptions along the domain for that?
No.
No. So it's continuous all the time. So if they say, does it exist? My answer would be, yes. Yeah. Now here's what a calculus student would have to do to prove the theorem. Step 1, they have to make sure that there's a point. So they plug in x equals 2, and they get 7. So check, they just found the point 2, 7. The point exists. Step 2, they'd have to figure out the limit from the left side and the right side. So you could do this a few different ways, but at first when they're exploring functions in calc, they have you use your calculator and they put it in ask mode for the independent variable. So Mrs. Gupta would have you approach 2 from the left side. Do you see what's happening on the x's? They're getting closer and closer and closer to 2, but they're staying underneath 2. And then she's going to do the same thing, but you're going to approach 2 from the right side. So closer and closer to 2, but sticking on the right side of it. And then she would have you look at all the y values. What limit does it seem to be approaching?
7.
7, yes. So the limit as x approaches 2 equals 7. So let's check. The limit exists. Step 3, does the point and the limit, are they saying the same thing?
Yes.
Yes, you got 7. You got 7. F of 2 equals the limit as x goes to 2. Check. Doesn't calculus sound fun?
Seems kind of easy, to be honest.
I mean, it's, you know what it is? This part of calculus kids are bothered by because they're like, well, duh, obviously, it's continuous. Why can't I just say it's continuous? Because Mrs. Gupta is trying to get you ready for the ones that aren't so obvious. So you have to go through the theorems and prove them. Welcome to upper level math, y'all. It's a bunch of proving things. Yeah. That just made a lot of you really nervous. They're like, proofs! Not those kind of proofs, different proofs. Okay. This one. This is more pre-calc speed. Now I'm going to walk through the calculus of it with you so you can see how they're going to prove it's discontinuous, and then we'll talk about how a pre-calc kid would have thought about this. A couple lessons ago, do you guys remember us talking about rational functions like this? Or any functions I was going to give you, and I said there's 2 things you need to look out for domain interruptions. Even radicals and denominators. Because what's the problem with having an algebra denominator? Do you remember what your denominators cannot equal? 0. So a pre-calc student would have just said, well, x squared minus 1 cannot equal 0. And then they would have figured out the problem area. And you guys would solve it, and you'd find out that x can't be positive and negative 1. And right now, with your pre-calc brain, maybe you don't know what happens at positive and negative 1. You just know that something goes wrong at x equals positive 1 and x equals negative 1. And that's okay for now in pre-calc. Later on, when we actually look more into rational functions, we'll talk about why this is happening. But for now, the quick answer for pre-calc is no, it's not continuous at 1 because something happens. Let's talk about what happens though. In calculus, if you tried to plug in a 1 right here, you'd get 2 times 1 on top, and then you'd get 1 squared minus 1 on bottom. What y'all gonna get? 2 divided by 0, which is like something happens, like the earth explodes or something. I don't know. It is undefined. There's some sort of, that says undefined. There's some sort of domain interruption at x equals 1. The function is not defined there. So right away, the question of, is it continuous? The answer is no, no, no. So then they extend it in calculus, and it says, what kind of discontinuity do you have? So I kind of breezed over this a minute ago, but there's something called an infinite discontinuity, a jump, and a removable discontinuity. You guys are not responsible for knowing what kind of discontinuity it is right now. But this is what calculus would have you do. Mrs. Gupta would have you approach it from the left side. X equals 1 from the left side, and then also from the right side. Look at what's happening to your y values on the left side. Negative 9.5, negative 99, negative 999. What do they seem to be approaching?
I don't know. 1,000?
Do you think it'll stop at 1,000?
No.
It'll just keep going, don't you think?
Yeah.
Can we call that negative infinity? It's just going to get more and more negative as you go on? Okay, on the right side, what does it seem to be approaching?
Infinity.
Positive infinity. Now, I know they both have infinities in them, but are they the same place? Negative infinity and positive infinity? No, no, no. So, since you're approaching 2 different values, or even 2 different parts of the number line, this is definitely a discontinuity, and because they're both approaching infinities, this is called an infinite discontinuity. You are not responsible for knowing that that's called an infinite discontinuity. You just have to know that there's something wrong at x equals 1. Later on, we'll learn it's an asymptote. That guy! You have seen these. So here's my 2 questions I warned you about. First question, do you remember how to graph a piecewise function? If you do, that's amazing. We're going to relearn how to graph a piecewise function in a couple of days, next week. But a little rehash for y'all. Piecewise functions. You don't have to graph this, guys. You can just watch the magic happen. At x equals 2 is the domain place where something happens. Pretend that's x equals 2. If x is greater than 2, the function behaves like the line 2x plus 1. So if I actually started at x equals 2 and I plugged it in, that would be 2, 5. But why would I be putting an open circle here, by the way? Look at your domain over here. It says x is greater than 2, which means you don't actually have a point at 2. So I still draw something and draw an open circle. And then you would give me some points that were greater than 2, like maybe you'd plug in a 3 or a 4, and you'd end up with this line, or array I should say. The other piece of your piecewise function, if you start at x equals 2, you get 2 comma 1 with a point. But now you can only give me numbers that are less than 2. So after I either plug in some numbers that are less than 2 or I just continue on with slope, y'all end up with like this. Ooh, that was not straight. Okay. So look at x equals 2. Does this look continuous to you? Here's what we call a jump. This is a jump discontinuity. So now that you all remember how to graph piecewise functions, how many of you would love to graph every piecewise function you encounter? Oh, none of you? Oh, you're weird. You just really love piecewise functions. Do you think they're fun? Well, reserve your opinion until you learn how to do a PreCalc piecewise function. They're not going to be lines anymore. They're going to be quadratics and such. It's going to be fun. We'll save that fun for next week, though. All right. So, except for Daniel, the rest of us say, no, thank you. We don't like graphing piecewise functions. There must be an easier way. And there is. All I need you guys to do for me is to figure out what happens at x equals 2 for both of your functions. So even though it's not technically defined here, do you guys remember there were cases where sometimes the pieces matched up and they did have an overlap of sorts? So if that happens, it's continuous. If it doesn't happen, there's a discontinuity. So what I would have done, because I'm lazy, is I would have plugged in a 2 and got 2 comma 5. And then I would have plugged in a 2 right here and got 2 comma 1. And then I would have said, self, are they the same? And then I would have said no. So this is why it is discontinuous at x equals 2. You're getting 2 different output heights, depending on which piece of the piecewise function you were at. I plugged it in the blue function, 2 times 2 plus 1.
Oh.
Yeah. So that's how I would expect you guys to evaluate that on your test. I don't expect you to be graphing piecewise. It would just be plugging into both parts of the function at that domain. This question's a little silly. So I don't think we need to do a lot of work, guys. Who is that? What shape is that? It's a quadratic. It's a parabola, right? You know, something like this. And it asked me, is it continuous?
Yeah.
Yeah. So no matter what x value they gave you, the answer is yes, it's continuous. Now, you can go on and you can find what happens when x equals 4 by plugging it in. Let's see, that'd be a 16 plus 20 plus 3, so 39. They didn't really ask me that. I was going above and beyond at that moment. If I was in calculus, I would have to prove those 3 things. So we just found the point, check. Then I'd have to do the limit thing from the left and the right side, check. And then I'd have to prove that they matched, check. It's going to be fun, right? Can't wait to take calculus. All right. This theorem, okay, this is another duh theorem, but that's because you guys have so much technology at your hands that this theorem seems really like pointless. This theorem used to have an immense amount of help when you were doing these by hand. Imagine, guys, finding zeros of polynomials without a graphing calculator. Sometimes it's amazing. Sometimes you can factor them. But what if they're not factorable? Ah! So there's a huge theorem in algebra called the fundamental theorem of algebra, which ties in with the fundamental theorem of calculus at certain points, that would incorporate when your function has an x-intercept. So that way, instead of like doing lots and lots of math, you could at least narrow down your window and say, I'm pretty sure something happens between x equals 4 and x equals 5. Okay? So it was giving them a way to estimate and prove that something happened. Let me explain this theorem to you for a moment. Look right here. They filled out a table. And when x equals -3, your function's way down here at -13. And when x equals -2, your function pops up here to like 2. Think about this, guys. In between these two red points, what do you know must occur if it started at -13 and it ended at 2? What did it have to have gone through in order for that to happen? It must have a 0, right? It had to cross the x-axis somewhere. Are you okay with me saying that? If it starts negative and now it's positive, it had to cross through 0 at some point. That's the theorem. And you're like, uh-huh. So back in the day, that was a really cool theorem. It's not so cool anymore. So when you guys get to your bookwork and they refer to this theorem, what we're going to have you do, and I'm going to show you an example later on in the lesson, we just want you to find the x-intercept. We want you to find the 0 using your calculator. Okay? So I know it's between -2 and -3 somewhere. Do you guys remember us doing that left-bound, right-bound business? That's where those come in handy. If you know it's before -2 but after -3, those are your left bounds and right bounds. So instead of scrolling left and right, you can just hop. So you are using that theorem, you just didn't know what to call it. All right, end behavior. All right, first thing I need you to do, some terminology that we all have to get familiar with. Are y'all okay if when I move this direction, I say x is approaching positive infinity? Are you okay with me saying that notation?
Yep.
Heard that before? What about if I travel to the left? That means x is approaching negative infinity. Yes, yes. Now, ignoring the limit notation, we're not worried about that. What if I'm going upwards?
Infinity.
And who is approaching infinity?
Y.
So we're going to fancy talk, call that f of x. And then as I go down, that's f of x approaching negative infinity. So these approaching arrows that you're using are actually a calculus notation. So good job, Algebra 2. You learned a little bit of calculus back then. This is fancy talk for right. This is fancy talk for left. This is fancy talk for up. And this is fancy talk for down. It would be so nice if we could just write right, left, up, down. We can't. So first thing you need to do for me is... okay, where's my extend page? Well, whatever. You need to replace your end behavior. There's a backwards thing on your notes. I want you to scribble it out. I think it's right up in this box. I think it does it backwards. This is what you're supposed to have for end behavior. So let me write that a little bigger. Ah, that did not help.
Really?
That's helpful. Just draw lines through it. There we go. Gosh, be golly. I don't even know where my... There we are. Extend page. All right. Hold on a minute. I feel... Alright, so end behavior template. And this is that thing you had to write 100 times in Algebra 2 and you were like, oh, is there a shortcut? And your teacher should have told you, this is the shortcut. The actual end behavior is much more elaborate. So, f of x approaches blank as x goes to... Now, I, being the dyslexic I am, always puts x goes to negative infinity first. Because if I start changing the order in which I look at end behavior, things go poorly. So make sure that template is written on your notes. That is the template I want to see every time we're doing end behavior. Come on, pen. And then I need you guys to translate this for me a little bit. As x goes to negative infinity is a fancy way of saying? As the left side, yep. And then as x goes to positive infinity is a fancy way of saying? Right. Technically speaking, you can switch around the order, but what you have to make sure you understand about end behavior is that this row, this is one end of the end behavior. These go together, as does this row. So, dyslexic lady over here always does left behavior first. because I don't want to mess up. Alright, so with that being said, I don't like when they're written side by side like this, so if it bothers you, you can rewrite it. But because I'm stuck in my ways, I'm going to ask you to determine the left end behavior first. So I was told my Algebra 2 kids to pretend you're a little bug, and you're traveling along the far left side of your curve. Where are you going? Oh, look at you being fancy. I was expecting you to say down, but you all went with negative infinity. Nice job. All right. And then for the other end behavior, that would be as x goes to positive infinity, which we know means right. All right, little bug, you're on the right side of the curve. Where are you going?
Up. Up.
Northward, up. Also known as infinity. Now, do all end behaviors look like that?
No.
No, of course not. The part I wrote in blue will not change, because you always want left and right end behavior. But the up and down thing is going to change depending on what the degree is and what your lead coefficient is. So here we had a cubic polynomial with a positive coefficient, so the left side went down and the right side went up. I'm sorry, my phone's going off. Yes, if there was a reflection, you'd see the opposite. Now, just for funsies, does anyone remember what happens when you have an even degree, like an x to the second power or an x to the fourth power? Okay, yes. So your ends are either going up, up, or what else could be happening?
Down,
Down, down. Okay. So there will be a point in your life coming up soon where I expect you to know the nature of the question, like the end behavior, without graphing it. Like you should be like mentally graphing.
What?
Yeah. That's coming up soon. So here, they were very kind to you. They said you have a negative x to the fourth power minus 2x. They went ahead and graphed it for you, but Cameron already spilled the beans and said if you have an even degree and with a negative coefficient, we knew the ends were going to go down, down. So here's the annoying part. Yes, you have to write the end behavior template all out. This is the shortcut. So I'm going to do left behavior first always, because that's me. So a little translation here, guys. On the left side, where are you going? What do we call that? Fancy this time. Negative infinity, very good. And then on the right side, where's he going? Also negative infinity. And you'll see that when you have an even degree polynomial, the ends will be going in the same direction, and either up, up if it's positive coefficient, lead coefficient, or down, down if it's negative. If you're not familiar with those right now, it's okay. You do have a graphing calculator. Oh, this one. All right. This one's fun. Mrs. Hoffbauer is suggesting that we check everything numerically on the calculator, and we will do this in a moment, but let's explore the graph for a moment. Write down your end behavior template. Wasn't it nice in Algebra 2 when they wrote this template out for you? For a while, at least. So nice. Yeah, that won't happen anymore. All right. So I want the left side, and then I want to talk about the right side. So when we get to the rational functions chapter, these will all make a lot more sense. But for now, let's just explore the graph itself. On the left side, it seems to be flattening out. Are you noticing that? It doesn't seem to be going up, up, up forever, but it's approaching what we're going to call later a horizontal asymptote. And I think something similar happens here on the right side. It seems to be flattening out. And I think they're flattening out to the same number. Anyone want to take a stab at what number you think they're approaching? It's just a guess, because you think it's 5? Okay, here's how we're going to confirm it. We're going to go to our calculator, and we're going to type our function. Now be careful when you type a rational function. If you have more than one thing in the numerator or the denominator, you have to use parentheses. So make sure you put parentheses around the 5x. And then divide by, was it x minus 2 in the denominator? Thank you. Make sure that is also in parentheses. And you can go to your table. There's nothing wrong with going to your table and plugging in some numbers that get really, really big and really, really small. I'm going to cheat, though. I just want to go to the graph hit zoom 6 to come back to a normal window. And instead of me plugging in numbers that get really, really big or really, really small, I'm just going to use my trace. There's your little bug we keep talking about. So using your left arrow, make your little bug travel far to the left. And watch the ordered pairs at the bottom of your screen. It's going to adjust the window as you go. I think you guys guessing a 5 was really, really smart, because I think it is approaching a 5. Let's check from the other side now. I need to hop over here. So I'm going to type like x equals 5, just to get over there. And then little bug, travel to the right. Watch your y values. Yep, I think you're approaching 5, but from the top this time. So you guys are dead on with your guess of 5. We're going to learn algebraic ways to figure that out in a couple chapters from now. But yeah, 5 and 5. If you were using your table, what you would have to do is you'd have to plug in numbers that are very, very largely negative and largely positive. So what would be a good example of a number that is super duper negative? Negative 56. It's as big as you go. Can you go bigger or smaller, technically? Get crazy. How about like negative 100,000? That'd be pretty bad, right? And someone last hour plugged in a negative 3 million, and the calculator ended up calling it a 5, but when you actually hovered over the 5 with your cursor, we found out it wasn't 5. It was like 4.99999999999. So he got real close to what's considered the asymptote, but your calculator at some point is just going to say, you know what, let's just call it a 5, even though it's not a 5. There's just so many pixels in the screen, you know, it only can do so much. All right. Oh, well, this is a little boring. This is like an Algebra 2 question, guys. Can we skip it?
Yes.
Where's the end behavior going on the left? Up.
Infinity.
On the right.
Infinity.
Up. Yeah, boring. All right, move. Okay, this is a great question. There's one just like this on your test. I want you to think like a PreCalc student. I want you to think like a PreCalc student who had a lesson 2 days ago that was covering this. When you talk about continuity and you talk about what's called a rational function, you have to watch out for your denominators. Remember, guys, your denominator cannot equal a 0. That would produce what's called a discontinuity. You don't have to know what kind, just know that it is discontinuous if that happens. So y'all, if you plug in x equals negative 4 right there, what happens? You get a divide by 0, which we just said we can't have. So the answer to this question is it is discontinuous at x equals negative 4. You don't have to know anything other than that. You don't have to know anything about what is it approaching, the limit, nothing. Just discontinuous at x equals negative 4. Which also happens to be the domain interruption. Remember the other day we were doing domain and you guys would tell me x can't be negative 4 and then you'd write it as an interval. So these ideas need to start kind of connecting in your brain. They mean the same thing. All right, y'all, what kind of function is this? The cubic looks roughly like this. So any polynomial is continuous along the entire domain. So when it says, is it continuous at x equals 1? Well, that's a really easy question because it's continuous everywhere. So polynomials are always continuous because they have domain of negative infinity to infinity. So therefore, when I ask you a continuity question on a polynomial, yes, continuous at x equals 1. Now, it did not ask you to do anything further. It didn't say, well, if it's continuous, go tell me what it equals at x equals 1. It didn't. If you want to go figure it out, you go ahead, but it didn't ask me, so I'm going to skip it. All right. This kind of ties back to what we were just doing a few problems ago. We know with rational functions like this, if you have algebra in the denominator, you know this denominator can't come out to 0 because that would be a domain interruption, or in our words today, a discontinuity. So you can either plug in a negative 1 and plug in a negative 2, or we could go back to our lesson a few days ago. Can you guys solve that for me? It's factors, huh? This is x plus 2 times x plus 1, and if you tell me it can't equal 0, that means x cannot be negative 2, so no. And x cannot be -1, so no. Whoops, I don't know why I crossed that out. Okay, so you're going to tell me it is discontinuous at x equals -1 and x equals -2. I found that to be easier than like manually plugging in -1 and -2, but if you would rather do that, you sure could. All right, here is where, if you notice on your homework problems, 17 and 21 are starred. That's because on the purple sheet we had you change the instructions. The instructions in the book want you to use that weird theorem that states like, find the intervals where there must be an x-intercept. So they'd want you to go to your table and they'd want you to look at x equals -6, -5, -4, -3, -2, -1, 0, 1, 2. And then they'd want you to compare all your y values and determine when did it switch from positive to negative and point that out to me. Well, Hofbauer and I decided that's a little antiquated for the technology you guys have. Your technology actually finds the zeros. So that's what we're going to want you to do, is we actually want you to find the zeros. But we would like you to restrict them at least to between -6 and 2. So between -6, x equals -6, and x equals 2. So could we all remind ourselves how we do this? Go to your calculator. Type this into your y1. And then because they want me to restrict my window, I'm going to restrict the x's from -6 to 2. So follow me along that part if you don't remember how to do that. And I forgot what the function was. Okay. Of the x to third. And this one, you guys don't know how to solve it algebraically, so you really would be relying on your calculator to do the calculus magic. When you go to calculus, you'll find some other methods for solving. Hey guys, once you get your function typed in, go to Window, and then make your x's go from -6 to 2. You can leave your y's from -10 to 10, because all I really need to see is where it crosses the x-axis. Boom, boom, boom. All right. So we can kind of sort of use the theorem, guys. Tell me, between what two values is this guy? 1, 2, 3, 4. So between -5 and -4. So the reason I like this theorem is because it really helps you with that left bound, right bound stuff. When I go to find my intercept on my calculator by going to second trace and then choosing number 2, when it says give me a left bound, give the left bound that you just told me. Say -5. Boom. And then when it says right bound, give the right bound you just told me, -4. And then guess, just hit enter, and then you're going to get a really gross thing because it's not nice. -4.828. And then did anyone get this 1e -11 thing? Okay, so I'm going to remind me what that means. It's -1 times 10 to the -11th power. Yes, it's 0.000001. It's got like 10 zeros. I don't want to do that. It's 0. It's 0. Anytime that E shows up, it's a pixelation problem with your calculator doing calculus, and it's doing the best job it can, but the picture stinks. So it's 0. So just, we're running out of time here, guys, so I'm just going to spoil a little bit. On your notes, you might want to make a note. You're going to find the zeros by going to second trace, and then choosing number 2, the zero finder. But really concentrate on doing the left bound, right bound the way that we just did with the hopping. Try doing that. It's going to save you time and energy later on when we do a lot of these. These zeros were at approximately, where'd we go? -4.828. There's another one at -1, and there's another one at 0.825. And the questions on your homework, 17 and 21, are just like that. You're going to be finding your x-intercepts. All right, I want to talk about this Ohm's law question. I really like this one. So we have Ohm's law has a relationship between a resistor, voltage, and the current. So they define the variables for you up here. Resistance, excuse me. So the resistance is calculated by taking the voltage and dividing it by the current. And they want to know that if the voltage remains constant, but you keep increasing the current, what's going to happen to the resistance? Well, Someone give me their favorite smallish number that I can use for voltage, because I don't really... 2. All right, sounds good. All right, now what I want you to do is start plugging in large numbers and keep getting progressively larger. So, like, let's start with 2 over 75. What is that on your calculator? You know I don't do decimals in my head. 'What'd you get?
1.52.
No, child. Oh, wait. Is it?
0.026.
That's cool. All right. So go bigger. How about 2 divided by 750? I know, it felt good.
It's 0.20037.
Probably. Makes sense. How about 2 divided by, let's just get crazy, 9 million.
What the heck?
I don't even know if I wrote a million. Just pretend.
0, 0, 0.
Just divide by a really big number. And you're going to get scientific notation, aren't you?
2 times 2, 2, 2, 2, 2, e negative 7.
So that'd be like 0.00000. Okay. What is happening? What's it approaching as we get bigger and bigger? Yeah, it's getting closer and closer to 0. So it's approaching 0 for a resistance value. Now, is it ever actually going to get to 0? Not technically, mathematically, but if you think about like the way currents work, it's going to be immeasurable, like so small that they wouldn't be able to measure it anymore. And I don't really know a lot about electricity, but I feel like if you start like cranking the current, like you're going to blow something, right? Isn't that the problem? Like I don't know. Like I don't really understand how electricity works, I'm going to be honest. It's like it's a modern miracle to me. But something happens. I popped enough circuit breakers to know that something happens. Okay, there you go. All right, on homework, remember guys, you don't have to finish this homework, except I would most definitely do numbers 3 and 9 tonight because that's on your test on Thursday. This is not quite completed though. You also have to do numbers 23 and 27. I don't know why they got cut off. My bad. Eventually this whole homework assignment has to be done, but I wouldn't concentrate on it tonight. Got it? Tonight you should be finishing those 2 plus the review. And your homework check, that too. Wow, that was like Dr. Seuss. Did you catch all that rhyming?